Okay, we're on. So welcome everyone. Announcements. Let me get a good marker first. Just throw this one out. So I'm giving you another problem set today because, well, the semester's winding down, really. And we're gonna have two more problem sets. This one is gonna be, last one I think was the hardest problem set of the semester, maybe. This one will be easier, right? I don't wanna say it's easy, but it'll be easier. And I was deciding when to make this due. You know, it was short enough that 1 week seemed good enough, but I didn't want to make it due on election day. So I'm going to make it due on Wednesday. It's your first problem set due Wednesday. And you can send it in anytime Wednesday. And that gives you, if you're waiting in line for 4 hours to vote, being a good citizen, well, no one should ever wait in line 4 hours to vote, but if you have to, right? Then, you know, you have till midnight on Wednesday to do your problem set. How about that? Or you could work on your problem set while you're waiting in line. Right? And then you could be doing, you know, the two most productive things one could ever think of at the same time. Stat mech and voting, right? So how about that? Bring your problem set to the polls. Problem set 6. And if you bring your problem set to the polls, you can discuss it with people.
Yeah.
See if they have any.
I think people would love that.
Accessibility of science.
So problem set 6 is going to be due Wednesday.
Just so you don't know them. Like, I think that's a way to find the line. You just threaten
Start
them.
talking to them about, you know, like
you just-
derivation.
Right.
Yeah, just
Everyone will
discuss
let-
stat back. Everyone will let you through.
Right.
Although, if you're voting on campus, maybe not.
Yeah.
Maybe
They
on
might try
campus.
to make it-
Yeah.
It would be fine.
They'll bring their homework to you.
Exactly.
So that's everyone have that due Wednesday anytime. Just send it to me by email. And then my only other announcement is keep reading Macquarie chapter 11 is what we're on. Okay. So really, there's only. Sorry. Why did I say 6? I'm thinking 6 is what we just finished. There's really only 2 major topics we have left to cover. We're gonna have time to cover, really, which is our discussion of crystals, and then we can move on to the Ising model and Monte Carlo. And so hopefully we're gonna be done with crystals, well, next week, hopefully next Tuesday, maybe we'll go into Thursday, and then we're gonna discuss the Ising model. And that's gonna take us pretty much the rest of the semester. We may have time for a little bit of discussion on liquids, but we'll see. Okay, so we are going through phonons, right? So we started phonons last time. Oh, John, am I good right here?
Yep.
Okay, great. So we started phonons last time, and so we're doing phonons in crystals. Okay, is the topic, and we're really focused on the heat capacity, right? I told you our goal is to reproduce the low temperature and high temperature limits that we observe experimentally. And so where were we last time? Well, we were trying to get a Hamiltonian. Okay, so we're in the process of writing down a solvable Hamiltonian. And I like to remind us of where we are. Okay? And so what we did last time is we were working on a classical energy function. And so we talked about the relative coordinates of the atoms. We wrote down a orthogonal transformation, right? We wrote down a Hessian matrix. And so last time we ended with this expression, I think. We ended with E equals m over 2 c dot, right? This is a velocity vector transpose. M matrix, M transpose matrix, C dot, that's our kinetic energy term, plus 1/2 C transpose vector, M matrix. This is a K or kappa. I have to be careful. This is kappa matrix, M transpose C. Okay? Everyone remember this? If not, I understand. So what did we do to get this? Right? Where this matrix M is defined by the special matrix that diagonalizes our Hessian, right? Is defined by this equation, kappa equals M transpose K M, okay? And this is our Hessian matrix, right here. So these were the two equations we ended with, okay? So, do we remember this? Basically, we wrote down this Hessian matrix, which were all the second derivatives of the energy with respect to our coordinates. We said symmetric, so linear algebra tells us that there exists some matrix M, which is an orthogonal matrix, that diagonalizes K when we do this transformation. And so this is a diagonal matrix from this transformation. M is defined by the unique matrix which satisfies this equation, right? And then we all learned what phonons were last time, remember? We had this revelation, and we defined phonon coordinates. This M is a orthogonal transformation because its columns are orthogonal to each other, and so it's essentially a change as a coordinate transformation. And the phonon coordinates are defined by eta. Okay, so eta is a phonon coordinate. It's defined as M transpose times our relative coordinate C. And so that's what phonons are. These are our relative coordinates. We transform them with this matrix M, and we get some new coordinates eta. Okay? This is a linear transformation. Right? Anything you do in linear algebra is a linear transformation. Okay. So that's where we stopped. Now what we're going to do is we're going to write 3 more equivalent expressions from this equation, which we're going to use on this guy. So this implies the following. Let me just write it down, and it will be pretty obvious, I think. We could take the time derivative of this. Remember, I'm using a dot for time derivatives. This thing doesn't depend on time, right? Because this is just a constant matrix. So this is just constant. So if I take the time derivative, I get eta dot equals M transpose C dot, right? So basically, I can use the same transformation on the time derivatives of the coordinates. Okay? What else can I do? I can take the transpose of the equation. So if I take the transpose of the right side, I have to flip them and take the transpose of each. Everyone remember that rule? Okay. So if I can write eta transpose equals C transpose M. Okay, I flip them, I take the transpose of each. What else can I write? And then I can use this, I can take the time derivative of this one too. So I can write eta dot transpose equals C dot transpose M. Yeah. Right. Okay. Everyone good with those 3 equations? So now what I'm going to do is I have 4 phonon coordinate expressions. 1, 2, 3, 4. I'm going to use all 4 of these in here. Okay. So, let's put arbitrary labels on these. Let me call this 1, and let me call this 2A, 2B, 2C, 2D, right? And so we're going to combine equation 1 and 2A through D. So what are we going to do? We're going to look in this equation for products that look like these. So in my kinetic energy, I have a C dot transpose M that looks like this one, right? And this looks like this, right? So here I can substitute an eta dot transpose, and here I can substitute eta dot, right? So I can write E equals M over 2. I get this becomes this, eta dot transpose, okay? And these two become this, eta dot. Okay? And then I go to this term, plus 1/2. This looks like what? Right, this looks like eta transpose. Kappa I don't mess with. I like kappa. Kappa's diagonal. I like diagonal matrices, right? So we're going to leave kappa. Okay. And this one is eta. Yeah? Okay. So I've rewritten my energy function using these new coordinates. So all I've done is a coordinate transformation. This is my energy function in the relative coordinates C. This is my energy function phonon coordinates, right? So energy expression in phonon coordinates. Okay? And what have I gained here? Why is this equation much more useful than this equation? Yeah, because this matrix is diagonal, and so these are a bunch of uncoupled harmonic oscillators. So let's see that. Okay, so since kappa is diagonal, what this is this is a set of uncoupled, right? Before we had these coupled harmonic oscillators, now they're uncoupled. Okay, so let's see how this works out. Okay, so now I'm done with linear algebra. We've done a lot of matrix algebra. Now I'm going to backtrack, and remember I wrote my sum equations in terms of vector and matrix equations. Now I'm going to go reverse. So now I'm going to write this in terms of summation and get rid of my vectors and matrices. So to see this, write out sums explicitly. Right, so now I'm going to actually do my matrix multiplications. We went over this last time. I'm not going to write it out in too much detail. This is a dot product. Eta is a row vector. A row vector times a column vector is a dot product. So this is just a sum over I. We have 3n degrees of freedom. M over 2 eta I dot squared. Okay? Just every element of the row times the corresponding element of the column. This one is a double sum, right? And so we talked about this last time. This is 1/2 sum over I equals 1 to 3n, sum over j equals 1 to 3n. And we talked about this last time. This is eta I, kappa ij, eta j. Right? Everyone okay with that? We talked about how this double sum equals this vector matrix product. Okay, so this is just writing out the matrix multiplication, but now this is diagonal, right? But diagonal means that kappa ij is kappa I times the Kronecker delta function, right? It's 0 if I doesn't equal j. So that means that this whole double sum collapses. All the elements in these double sum when I doesn't equal j is 0, and so essentially this becomes one sum, just a sum over the diagonal elements, right? So therefore, E becomes, I have one sum over I here. This collapses into one sum, so you can collect everything and do the same sum. And so you get E as a sum over I equals 1 to 3n. And now I'm going to collect my kinetic and potential energy together. The kinetic energy is the same, m over 2 eta I dot square. This, I pick out the diagonal terms, which are just plus kappa I over 2, 1/2, and then I have eta I square. Okay, so that's what my energy is. Everyone okay with that? And so now, right now it's easier to see that this is just basically a sum of energy expressions from each phonon I, right? Each phonon I. Do the phonons have the same energy or different energy? What's going to determine the energy of the phonon? In this, the mass, right? But the mass is the same. This thing,
The force constant.
the force constant. Are these going to be the same for every eye, or different, or?
They should be different.
It should be different. There's no reason to think they're the same, right? So note that every phonon will have a different energy in general, right? Every phonon will have different energy as determined by basically the force constant kappa II, right? Or we know it's a harmonic oscillator. Harmonic oscillators are characterized by frequency. Anyone remember how you get the frequency from the force constant? We did it once. Root k over m, right? Or we can write a frequency omega I equals square root kappa I over m. Okay? And so essentially they will have different energies depending on the force constant. Okay, so we're done with our coordinate transformation. This is nice because we can do the harmonic oscillators independently, but we've done everything so far from quantum mechanics, right? Our procedure for doing stat mech is solve the Schrodinger equation, put the solutions of Schrodinger equation into the partition function, right? So we'd like to follow that procedure. This is classical mechanics, right? We don't have velocities in quantum mechanics. We have momentum operators. And this is an energy function, it's not a Hamiltonian operator. And so what we like is a quantum mechanical Hamiltonian that corresponds to this classical expression. And there's ways to do it rigorously. I'm just gonna hand wave a little bit, okay? So we're gonna obtain the corresponding, right, we've done everything classically so far, but we're going to use a trick to get the quantum mechanical Hamiltonian from what's called just quantum classical correspondence. Okay, and I'm just going to write it down. I'm not going to prove anything here. Right? We would like a quantum Hamiltonian. So the question is, we've done a transformation. So to write down a quantum Hamiltonian, you need a corresponding momentum operator for every position. Right? And so we've essentially transformed from a picture where we had Cartesian positions and Cartesian momentum. Okay, so these were Cartesian. Right? We started with all the atomic coordinates. We know the momentum operator for Cartesian coordinates, right? Minus I h bar d dx. Right? But we've done a transformation now where now we're in phonon coordinates, eta I, and the question is, what is the phonon momentum? And we're going to call it capital P, right? But the question is, what is this thing? If we knew this thing, then probably we could write down a Hamiltonian using a momentum operator, right? And so the question is, can we write the question, are we allowed to write call it a phonon momentum operator Pi equals minus I h bar d eta I. Can we do that? Right? If we could do this, then we just put our momentum operator in for the velocities, and we have a quantum Hamiltonian. Everyone agree with that, right? And so this is the question, and the answer is we don't know until we invoke some properties of classical mechanics. And so the answer is yes, if the transformation we did is a special kind of transformation called a canonical transformation, and it is. Okay, and really there's no way I can prove that unless we went through a lot of classical mechanics. Okay, so I'm just going to state it as a fact. So for specific, classical mechanics tells us, okay, tells us that we can do this for any canonical transformation. Okay? And this is kind of a circular definition. Because really how you define a canonical transformation is any coordinate transformation that preserves this fundamental relation between position and momentum. This is just the uncertainty principle. You'll kind of understand. Anyway, think about this. This is really the uncertainty principle. If you write down the uncertainty principle, it tells you that the momentum has to have this form, essentially. So a canonical transformation is anything that preserves the uncertainty principle between a generalized position and generalized momentum. It turns out that our transformation, our orthogonal transformation, M, right? The way we went from
this relative coordinate is essentially a Cartesian coordinate. We were just subtracting off the lattice positions. So our transformation was really M to get the phonons. And so the question is, is M a canonical transformation? And it is. Our orthogonal transformation, this, eta equaled M transpose C is a canonical transformation. It's one type of canonical transformation. Okay, so I'm just gonna have to tell you that because we don't know enough classical mechanics to really prove that. If you're interested, Google something called the Poisson bracket. Has anyone ever heard of the Poisson bracket? You'd have to take an advanced classical mechanics class. Okay, so you can Google what's called the Poisson bracket. It's an important quantity in classical mechanics that actually maps to a quantum commutator. So the Poisson bracket in classical mechanics is analogous to a quantum mechanical commutator. If you're interested in these canonical transformations, you need to know something about this. Okay, is everyone happy with that? That's rigorously what we would do. You have to trust me. Okay, so as long as everyone trusts me, then we're just gonna proceed, and we're gonna write down, using what I just said, we're just gonna write down a quantum Hamiltonian. Okay, so the quantum mechanical Hamiltonian in phonon coordinates. Okay. It's just what we already had, except now we're gonna use my trick that we're gonna replace the velocities with the momentum operator, which is this. Okay. So H, now it's a Hamiltonian operator, is sum over I equals 1 to 3n. Okay, all we have to do is substitute, this is p squared over 2m, right? So we just do p squared over 2m, and we get minus h bar over 2m. D squared, that should be an eta I squared. I should have h bar squared, right? H bar squared over 2m, plus kappa I over 2 eta I squared. Okay, so all I'm doing is substituting the momentum operator. And so now this looks like a bunch of harmonic oscillators, right? So this has the form H is a sum of single particle Hamiltonians. Okay. Let's put this in parentheses just to keep it straight, right? So everything in parentheses depends on one coordinate, eta I, right? So call whatever is in parentheses hi. Yeah? And so the Hamiltonian is just a sum of single particle Hamiltonians hi. Okay. And so we know how to do this. You know how to solve the Schrodinger equation for hi, because it's just a harmonic oscillator. This is just a dummy coordinate, right? You could replace eta with x at this point. It doesn't matter. And so you could solve this, and you know how to solve this partition function, right? Because we've written a rule for how the partition function behaves if the Hamiltonian looks like this. You remember?
It's 2 to the n over n factorial?
Close. We have to be a little careful. You're on the right track.
Yeah.
That expression is is true if all the q's are the same, right? But before we did that, we had a product of q sub I. And we only said it was q to the n if all the q's are the same. In this case, the q's are not the same. And so from before, we know that q, the partition function for the phonons, and the other trick is these are distinguishable because they have different energies, right? So the 1 over n factorial was if we have indistinguishable particles, but the phonons have different energies, so they're distinguishable. I can shoot neutrons at my phonons, and if my neutron has a specific energy, it's going to pick out one particular phonon. So they're distinguishable. So q equals a product of q over I, qi, okay? Where qi is a sum over single particle quantum states because we have harmonic oscillators. These have harmonic oscillator form. I'm going to use the quantum number n for harmonic oscillator, right? So qi is a sum of n equals 0 to infinity, the harmonic oscillator energies of e to the minus beta epsilon ni. This is the nth energy of the harmonic oscillator for phonon I, right? And the nth quantum state for phonon I, and epsilon ni, of course, is a harmonic oscillator. H bar omega I n plus 1/2. Okay? So basically we've written down the solution already. Right? Our solution is this. This is my q. The little q is this. And the e's are this. Right? And so let me just write this. Let me just write the note that these are distinguishable phonons because they have different energy. Right? And you might also make a note that this doesn't collapse to q to the n because these little q's are different. Okay, so we're essentially done. Let's think about what we want to derive from the partition function. And what I told you is we really want the heat capacity. So let's use our partition function and let's get the heat capacity. Let me go over here. Questions before I go to the heat capacity? This make sense? Okay. And actually, everything I've done is exact up to this point. I haven't made any approximations, right? The only approximation is that Taylor expansion we did for the potential energy, we truncated at second order, which is consistent with harmonic approximation. So as long as we can truncate the energy at second order harmonic approximation, this is exact. Yeah. So we're not making any approximation using phonons. Okay, so let's do the heat capacity. So, well, sorry. Let me write one thing else so we don't have to redo our work. We need this little q to put into this. We did solve for little q. We had a closed form expression for the sum. Who remembers what it was? We used the geometric series, right? We used the geometric series to solve this. And so we already derived a closed form expression for little qi. That little qi is e to the minus beta h bar omega I over 2 over 1 minus e to the minus beta h bar omega. Okay? So we already did this for our vibrations in a diatomic. So we can use that result. Okay. So this is all self-contained here. Okay, now we want the heat capacity. Okay. What is the heat capacity? Okay. The heat capacity is defined as CV is dE dt at constant V. So that's what we want. So what we're going to do is we're going to write down the energy first and take a temperature derivative. So first we need the energy. So let's write down the energy. We look in our Macquarie textbook for an expression for how we get the energy from the partition function. There's different ways to do it. Anyone remember this off the top of their head? I think he used it on a midterm. D beta A, D beta gives us the energy, remember? Right, so E is D beta A, D beta. Does that look familiar? Yeah. Okay, so this is the expression for energy in the canonical ensemble. A, right, is minus KT log Q. So beta cancels the K. I get negative here, and I get, this is negative D log Q D beta, right? Equals minus D log Q D beta. Right, everyone agree with that? Okay, now what I do is I substitute my expression for Q, which is the product of the little q's. So I have the log of the product of little q's, that's going to be the sum of the logs, yeah? So this is minus d beta, sum over I log qi, okay? Beta has nothing to do with the sum, so I can pull inside the sum, equals equals sum over I minus d beta log q. Okay? So we just need to take this derivative and sum it up. We did this derivative before, so I'm not going to go through the details. I mean, you could easily take the derivative using this expression, right? I'm going to skip the algebra and write it down. So I'm just going to write equals. I'm going to say as before. We've done this derivative. What you get when you do the derivative, you have a sum. You still have the sum over I. What you get is you get a h bar omega I times this thing in parentheses 1 over e to the beta h bar omega I minus 1 plus 1/2. Okay, that's what you get. We did this for the vibrations in the diatomic. We had the exact same expression for the energy. Okay? So that's the energy. And now we're going to get the heat capacity. So now take the derivative. Okay? So let's take this derivative. So CV is the temperature derivative of this thing, is d dt, the sum over I h bar omega I 1 over e to the beta h bar omega I minus 1 plus 1/2. So we have to take this derivative. Again, we pull the derivative inside the sum. The only temperature dependence is this exponent, right? So let's do it. Equals, we pull the derivative inside the sum. we have sum over I, h bar omega come in front. Okay. The 1/2 is gonna go away, so we have the derivative of this thing. Let's write it out. We're gonna have a fraction. So write a bar. So first you have this thing to the -1, the derivative of that is -1 times this thing to the -2, right? So we have this thing to the -2, beta h bar omega I minus 1 squared. We have a -1 here from that part of the derivative. Then we have to take the derivative of what's in the parentheses, right? And so we have to take the derivative of e to the beta h bar omega I. So it would help if, so I'm taking a temperature derivative. Beta is 1 over kT. So when I take the temperature derivative of this, I get a h bar omega over k. Okay, so I have a h bar omega I over k. And then I need the temperature derivative of 1 over T. So that gives me a -1 over T squared. Okay, and then I have the exponent itself. E to the beta h bar omega I. Okay, everyone see that? So then I can collect terms. So if I collect terms equals sum over I, this -1 is going to cancel with that -1. I have a factor of h bar omega here. I have a factor of h bar omega here, so that's a squared term. I have a t squared. I would like a k squared, because if I have a k squared, I could write h bar omega I over k t squared. I could pull all that squared, but I was missing one k, so I need to put a k out in front. Okay? Yeah? So that's a nice way to write it. If I bring a k out in front, then I have all this stuff squared. And then the only thing I have left is this exponential and my denominator. So e to the beta h bar omega I over my denominator. E to the beta h bar omega I minus 1 squared. Okay, so this is, sorry it's so low on the board, that is the heat capacity. Okay, so we are, that's an exact formula. Let me just write it one other way, because we're gonna have to make approximations. So this is true. Note we can also write CV as being K sum over I. I'm going to introduce a function which I'm going to call it f of omega. Okay? F of omega I. Okay? And this is true if this function f of omega is defined, if I define this function by h bar omega over kt squared times e to the beta h bar omega over e to the beta h bar omega minus 1 squared. Okay, so I'm just defining this function. And then obviously if you plug this function into, sorry, my circles got kind of messed up. If you plug this function into this formula, you obviously get this expression, right? Why am I doing this? Because the heat capacity is units of Boltzmann's constant, right? So this thing is unitless. And so what this thing is, it's the contribution of each phonon to the heat capacity. Right? And so this lets you see that the heat capacity of the crystal is just a sum of contributions from each phonon. Each phonon contributes an amount equal to F of omega I times K. Right? So the way you think about this is the contribution of each phonon to the heat capacity. Okay? So it's just a sum of contributions from each phonon. Everyone see that? Yeah? So, essentially our problem is solved if we know these frequencies. So our problem is solved if and only if we know the phonon frequencies. Right? So we have to know the entire set of omega I. And nowadays, this isn't really a problem. We know how to get these frequencies. How do we get them? We get the Hessian from DFT. We diagonalize the Hessian, and we get the kappa matrix, and we have the frequency. So fine, we can get them. But, back in 1900, I told you that this problem was first worked out by Einstein and Debye back in 1910. We didn't have density functional theory. They had no way of knowing these frequencies. Okay? And so they had to introduce approximations. And so what we're going to do now is pretend we don't have DFT, pretend we don't have computers, pretend we're Einstein and Debye in 1910, and can we come up with some approximations for these frequencies that let us get a approximate expression for the heat capacity that we can compare to experiment. Okay, so now what we're going to do is we're going to pretend that we're back in 1910. We are, and we'll see why we're going to be either Einstein or Debye, as those were the two people who worked on these phonon problems. We are Einstein or Debye. And this may seem sexist because I chose two men, but just wait. We're gonna be Marie Curie in a few weeks when we do the IC model, right? So we don't just have to be Einstein and Debye. Back in 1910, and we have no idea what the exact frequencies are. Okay. But we want to make some statements about the heat capacity. How to proceed? So we're going to introduce a couple approximations that let us guess what these frequencies are using something called dispersion relations, relating frequency to a wave vector. But before we introduce these approximations, we're gonna do another transformation on this equation. Okay, so let's first transform our expression using properties of delta functions. And it's not really clear why I'm doing this now, but you'll see why later. Okay. So I want to transform this, and how comfortable are people with properties of Dirac delta functions? Let me just go over it. Okay, so you can either put this in your notes, or I'm going to write this down as an aside, right? Because I don't really want it to break up our discussion. So let me just write an aside over here, and let's talk about a few properties of Dirac delta functions. Right? There's two types of delta functions. Where there's Kronecker delta functions, which are for discrete sums, and there's Dirac delta functions, which are for continuous functions. Okay. So what is a Dirac delta function? Well, there's different ways you can define it. One way you can define it is take the limit of a Gaussian function as the width goes to 0. So one definition, okay, is this. A Dirac delta function, we use this symbol. We're going to think of one coordinate, x minus a. And so it's a function of x, but it's centered on a. Okay, so it's centered on a. Okay. And you can think about it this way. You can take a limit as the width, the standard deviation of a Gaussian. Sigma goes to 0. It becomes more and more narrow. Of a normalized Gaussian, the normalization is 1 over root 2 pi sigma squared. And then we have a Gaussian e to the minus centered on a. So x minus a squared is a Gaussian centered at a over 2 sigma squared. Okay, so this is a normalized Gaussian. Okay? So then you have a picture of what the delta function is on your head. It's a Gaussian that's getting really, really narrow, right? Usually what we use delta functions for is just two rules, right? So there's two rules that we usually invoke, and that is a normalization. Because we're taking a limit of a normalized Gaussian, the delta function better be normalized, right? So the normalization is this, is that if we integrate from minus infinity to infinity, dx delta x minus a, we must get 1. Okay. So, I mean, the values of a delta function are essentially 0 or infinity. So delta x minus a is really a two-value function. It is equal to infinity if x equals a, right? Because the Gaussian gets higher and higher as it gets narrower. It has to stay normalized, right? Or equals 0 if x doesn't equal a. Right? So it's just a sharp function with a spike at x equals a, but it's a special kind of infinity. It's an infinity that obeys this normalization. Okay? This has to be true. But usually what we use delta functions for is the property when we integrate them with another function. Okay, so I guess we call this an integration rule. And this is what we usually use, okay? If we have a function, if we integrate from minus infinity to infinity, and we have any arbitrary function, I don't care what it is, call it f of x, and we multiply that by our delta function, delta x minus a, what the delta function does is it picks out the value of f at a. This equals f of a. Okay. And so this is probably the most useful identity that we use for delta functions, right? And the reason it picks out f of a is because it only has non-zero value at a, and normalization implies that it must have normalization 1, so it must pick out f of a times 1. That's the reason that works. Okay, so those are just the properties of delta functions that we need. If you've seen that, great. If you haven't, we'll just use those properties. So what we're going to do is we're going to take this expression and introduce a delta function here. Let me show you what I mean. Let me just rewrite this expression. CV is k sum over I f of omega I. Okay? And what I'm going to do is I'm going to write f of omega I using this identity. We're going to write f of omega I. I'm just going to substitute this identity, substituting little f for capital F, equals integral from minus infinity to infinity, the omega f omega delta omega minus omega I. Okay, everyone see that? I'm just using this property of delta functions to write f of omega I as an integral of a dummy frequency variable times this function f, which is just this, of a dummy frequency variable times my delta function centered at my frequency omega I. And then, this follows from this rule, but all my omega i's are positive. I can't have negative frequency, okay? Because all omega i's are positive, okay, this simplifies. I can drop that lower infinity and just integrate. I can drop the minus infinity and integrate from 0 to infinity. It simplifies to f of omega I is just integral from 0 to infinity instead of negative infinity to infinity. The omega f omega delta omega minus omega I. Okay?
So we're saying that each contribution is continuous?
We are saying that each contribution is f of omega I. Okay?
Right.
We're doing a transformation that lets us use a continuous variable omega instead of omega I.
Mm-hmm.
And we're going to transform to a density of states picture. So let me answer that question in like 3 minutes.
Sure.
I think it would become more obvious. So let's take this expression now and put it back in for the heat capacity. So substitute this form into this, right? So here CV equals K sum over I. But now I'm going to substitute this in for f of omega I. Sum over I, integral from 0 to infinity, d omega f omega delta omega minus omega I. Okay, just substituting that in. Now what I'm going to do is switch the sum and the integral. Okay, because I has nothing to do with the integral over omega, so I can switch them. CV equals K, integral 0 to infinity. I can move the sum all the way in to the only thing that depends on I. The only thing that depends on I is the delta function. So I can move the sum past the d omega, past the f of omega, and hit the delta function. So it equals this integral d omega f omega, right? And then in parentheses, I'm going to put sum over I delta omega minus omega I. Okay, so now what I'm going to do is just write a this is sum over delta functions. I'm going to call this a new function. So I'm going to define, what am I going to call it? density of frequencies, normally you would call this a density of states, but we're just specifying frequencies. We call this a density of frequencies. Okay, I'm going to use the term G. G of omega is just a sum. It's a sum over I delta omega minus omega I. Right? It only depends on omega because I'm summing over I, so I take out the dependence on I after I sum over I. Right? And so then if I make this definition, then I get a simple expression for CV. Deceivingly simple, right? So then I get CV is then just equal to K integral 0 to infinity d omega f omega g omega. Right? With G defined this way, and F, we already know what it is. Right? And so the picture here is that I'm just going from a picture of finite frequencies to a continuous variable. Right? So here I'm saying I need to know all the frequencies I sum over all the frequencies, each frequency contributes this much to the heat capacity. Now I say, okay, I'm just going to integrate over all possible frequencies. This is essentially the number of phonons near this frequency, and these phonons contribute that much to the heat capacity. That kind of makes sense? This is picking out. Right, this is essentially picking out the number of phonons at this frequency, and all those phonons contribute this much to the capacity. So what does G look like? Okay, so note that for finite number of atoms, N, right? G is going to look like, it's going to have discrete peaks, okay? G of omega has discrete peaks, okay? It's going to have a peak when there's a phonon, it's going to be 0 when there's no phonons, right? If there's no phonons at omega, G of omega is 0. It's only non-zero if I have phonons at omega. Right? But in the limit n goes to infinity, we have an infinite system, G of omega becomes continuous. It becomes a continuous function. Of omega. Okay? One thing we have to be careful with is normalization. Okay? Okay? Be careful with normalization. Okay, how many phonon modes do we have? 3n, right? Whenever you do a coordinate transformation, you end up with the same number of final coordinates as initial. We always start with 3n coordinates, so no matter what transformation we do, we're going to have 3n coordinates. So we have 3n phonon modes, and so G of omega must reflect the fact that we have 3n phonon modes. And so normalization is this. If we integrate from 0 to infinity, d omega g omega, okay, let's do this. We get integral from 0 to infinity d omega, plug in what g of omega is, it's this sum sum over I equals 1 to 3n delta omega minus omega I. Okay? Now reverse the previous trick. Now pull the integral inside the sum. Equals sum over I equals 1 to 3n. Pull the integral inside the sum. Integral 0 to infinity d omega delta omega minus omega I. I use my normalization condition that I just erased. Right? The integral of a delta function over all values of variable is just 1. And so this integral is just 1 by normalization of the delta function. Equals sum over I equals 1 to 3n of 1 equals 3n. Okay? So if I integrate g of omega over all frequencies, I get 3n, right? Because I need to get the total number of phonons. That's why it's called the density of frequencies, right? Or density of phonons, because if I integrate over all frequencies, I must get the total number of phonons. So essentially what's going to happen is Einstein and Debye are going to introduce different expressions for g of omega, but they have to be careful that they obey the normalization condition, right? And so the whole purpose of this transformation, everyone agree with at least the mathematics, even if we don't quite see the physical reason why we did this? Okay. What is the physical reason for doing this? For this transformation. Well, the physical reason is if I use this formula, I need to know all the omega I. Okay? If I use this formula, I just need f, we know f, right? F is this. We don't know g. Well, we know g if we know all the frequencies, but that's circular. Right? The point is we went to this because we don't know the frequencies. So because we don't know the frequencies, we don't really know what g is. But g is just a function of omega. It has a shape. Maybe we can just approximate g. Right? If we can dream up a function that's, physically realistic for g, then we just plug it in here and get the heat capacity. So that's what we're going to do. Right? This transformation allows us to dream up approximations for g. I mean, maybe you don't know how to do that, but I mean, you believe me, right, that if we can dream up an approximation for g, we can get the heat capacity. So that's what we do. Physical reason for this transformation is if we can introduce an approximation for this density of frequencies, g of omega, okay, we can approximate the heat capacity. Okay, so that's why we're going to do it. And that's what Einstein and Debye did back in 1910, right? They knew this formula. They didn't know the frequencies, but they each dreamed up a different approximation. Who do you think did a better job? Who do you think did a better job here, Einstein or Debye? You want to say Einstein, right? Because Einstein was the most famous physicist of all time.
I don't know Einstein for doing all this.
Einstein was amazing, right? Because Einstein made seminal contributions in so many areas, right? Brownian motion, photoelectric effect. Even without relativity, Einstein was a phenomenal physicist. And then you add relativity, and it's just mind-blowing. Anyway, Debye ended up doing a better job here. Einstein was busy dreaming of relativity, so maybe that was distracting him. Okay, and so what we're going to do is we're going to look at Einstein's approximation for g of omega, see what happens, and we're going to look at Debye's approximation. Einstein puts in a pretty trivial approximation. Debye uses continuum mechanics. So Einstein's easy. To do Debye, we have to do continuum mechanics, but it's not that hard. Okay, so we'll do both. So let me show you how this works. So we're gonna first, and I know I only have 3 minutes left, but I think if I write this down, it will solidify what we're gonna do. So this is called the Einstein model of phonons. Okay, and all it is really is Einstein's approximation for G of omega. Okay, and so what Einstein did is, suppose they all have the same frequency. That's the easiest thing we could do, right? So what we know is that a real crystal has 3n phonon modes of different frequencies. You know, and we said this before, the reason they have different frequencies is because the Hessian matrix has different diagonal lines, right? And this is that the Hessian matrix kappa II are different. The diagonal elements are not the same. Okay, but what if we just ignore this? Let's just ignore it. So Einstein's approximation, all frequencies are the same. Okay, we're just going to ignore this difference, and we're going to say, you know, this is back in 1910. Might as well make the simplest approximation if you're doing something for the first time. So all frequencies are the same. What that means is that omega I no longer depends on I. It's the same for all the phonons, so we can just call it omega naught. Okay? There's no dependence. All phonons have the same frequency, omega naught. Right? And this is sort of a mean field approximation, right? The way to think about this is each atom experiences the same environment as the crystal, so each atom rattles around in the mean field of the crystal, right? That would be the interpretation here. Each atom rattles around in sort of a mean field of the crystal atoms. Okay? And I know I'm out of time here, but let me just illustrate what I mean by this approximation for G of omega, right? So if this is my frequency, then I can write down G of omega. Let me just do it real quick. We'll do this next time. G of omega is this sum over I times these delta functions. Okay? None of these, I can substitute in omega naught for omega I. Sorry, I'm running out of room. I'm almost done. Equals sum over I delta omega minus omega naught. Nothing here depends on I, so this is just 3n times the delta function. Equals 3n delta omega minus omega naught. Okay, so I'll start there next time. I just wanted to illustrate this approximation gives Einstein an expression for G of omega, which is this, that he can then plug into this formula and get heat capacity. So that's what I mean by making approximations for G of omega. Okay, great. So we'll start there next time, and we'll go through Einstein's approximation. We'll see that indeed Einstein was not 100% perfect all the time, even though he's very good. And then we'll have to see what Debye did to fix it.
Daniel,
Yeah.
I have a question. Why is G of omega not a Kronecker delta for finite n?
Why is it not?
Or like, why is it? Because Dirac delta is for continuous functions, right?
Right. We are
Is
using a
omega
Dirac.
still continuous, I guess?
We're using a direct delta because we want omega to be continuous.
Okay, even though, okay.
So we're saying that this is going to be a continuous variable. This is going to be the center of a delta function.
Mm-hmm.
And so we're using Dirac delta for the continuous variable, omega. It just depends on whether your independent variable of interest is continuous or discrete.